In this video, we'll be doing the question you see on the screen from the 2023 Leaving Cert Higher Level Maths Paper 1. If you're looking for a different question from this paper, there should be a playlist in the description below. And if you're looking for a different paper entirely, have a look on my channel. I'll be doing all of this on a whiteboard, hopefully just like you're used to your teacher doing. But remember, we are on YouTube, so take advantage of that. Pause, try the question first, and even change the speed of the video to half speed or 2x speed if that's your thing. If you find this video or any of my videos useful, I would greatly appreciate a like, a subscribe, or especially sharing it with someone else you think might help. It might help. In question 3, we are asked to prove that square root of 2 is a rational number. So what does it mean to be a rational number? A rational number can be wrote as two integers dividing. So let me write that, let me do what we're going to do later on. Square root of 2 would be equal, we'll assume it's rational, and would be equal to a divided by b. Two numbers dividing each other, and where a and b are elements of z, they're integers. Also, we'll say this is the smallest two numbers you could get, because we can just assume that. For example, like 4 over 8, we'd never have to write 4 over 8. We could write, 2 over 4, but again, we'd never write that. We could write 1 over 2. There is any number that's rational will have a smallest fraction, a fraction where the two numbers have a common denominator of 1, or don't have a common denominator, I guess. So we'll assume that square root of 2 has one of these. Every rational number does. So to prove square root of 2 is not rational, we're going to show something's wrong here. We're going to just assume it is and show that something goes wrong when we play around with this a bit. Now, whenever you have a square root, one of the most common things to do, it's no different here, we're going to square both sides to get rid of it. So if I square both sides, I get 2 is equal to a squared over b squared. Again, play around a bit here, and we got 2b squared is equal to a squared. In question 3, we are asked to prove that square root of 2 is not a rational number. To do that, we're going to make the assumption that it is a rational number. So let's talk about what a rational number is. So like I said, let's assume it is a rational number. A rational number is a number that can be wrote as two integers dividing. So a divided by b, and like I said, where these are both integers. So I write that as a and b is an element of z. They're just both integers. And they're also the smallest integers they can be. What I mean by that is, instead of like 3 over 6, 3 over 6 is the same as 1 over 2. So whatever two numbers are here, they're the smallest they could be. Because obviously there's infinite number of fractions going this, multiply this by 2 or any number you want. You can get infinite number of fractions that are the same. But we're going to say they're the smallest they can be. And again, we're just assuming, so this works. I'll talk more about that at the end to strengthen up that idea. But that's how we're going to go about this. Okay, what is not a rational number? I'll talk about that as well. Some famous examples is square root of 2, pi, and e. They're not rational numbers. They're numbers we just can never get them with fractions. So square root of 2 is just a handy one we can prove. So let's go into that. When we have a square root, the most common thing to do is just square both sides, and no different here. We're going to square both sides. We get 2 is equal to a squared over b squared. Let's multiply both sides by b squared. We'll get 2b squared is equal to a squared. At this point, we have a leap, a very smart leap. I'm not sure who the first person to prove this. I think it might have been a Pythagorean back in ancient Greece times. But the leap here is to notice that a squared must be even. And that's because it's equal to a integer multiplied by an integer, which is an integer, and then multiplied by 2. And you multiply any number by 2, you'll get an even number. So b squared has to be a number, multiplied by 2, we have to be even. So I can now say a squared is even. Now remember what a squared is. It's a multiplied by a. And that means it's two numbers multiplied by themselves. The only way to get an even number in that case is if A is even. Two odd numbers multiplied by themselves are, or two odd numbers multiplied is an odd number. Two even numbers multiplied is even. Or hell, any even number multiplied at any point is even, and they just happen to be the same. Whatever way we say it, A is even. Okay, but if A is even, that means I can rewrite A as A is equal to some letter, we'll say C. That's pretty much the definition of an even number. It can be multiplied by 2. Okay, so let's leave that for a moment. If we put that back into this point up here, and we go 2b squared is equal to, instead of A, let's put in 2c squared. This becomes 2b squared is equal to 4c squared. Divide them both by 2, and we get b squared is equal to 2c squared. Again, c is some integer now. This is very similar to what we have up here, except a squared was on its own here. Now b squared is. So by the same logic I did here, I can say b squared is even. I can say b is even. I can say b must be equal to 2 times some number. And we call that number d. At this point, if we put that back right into the beginning, we break one of our assumptions at the start. Right at the beginning, I said square root of 2 is equal to a over b. But now I know a is 2c and b is 2d. 2 divides 2, this is equal to c divided by d, where c and d are smaller than a and b. But at the start, I assumed that I had the smallest fraction I could get up here. And this breaks that assumption. That's enough. That's enough to prove that square root of 2 is not rational. But to talk about a bit more, square root of 2 equals c over d. I could start this again with c and d, and at the end of it I would get, well, it's also equal e over f, where they're both half the size again. And I could stay going on forever and ever. And if you think about that, that means that whatever number I started with must have been so big that I could get half of it every time, forever and ever. And there's no number that exists that's so big you can half it forever and stay going, except for infinity. And the idea that square root of 2 is equal infinity divided by infinity is a bit ridiculous as well. That's clearly not what we're looking for. So something breaks down. And what breaks down is the idea that we could have wrote this in the first place. Square root of 2 will never be equal to a divided by b, where both of these are integers. So we've proven square root of 2 is not rational. In part B, we're given this nasty looking equation with lots of different logs of base 3, 9, 27 and 81. We are given a hint that we can change the base of any log. It's in our formula book. Log to the base a of b is well, whatever. You can look it up in the formula book. It's also in the question. They want us to get t out of all of this, and t is the only unknown, so we should be able to do that. And they want to have it in the form of 3 to the power of something. Okay, that's the information we've been given. Let's use the hint they have given us to change the base of some of these logs all to the same one. And you can use any base you want. 2 of them will work out well for you. Log to the base 3 will work out quite well. I guess log to the base 3, log to the base 9, log to the base 27 and log to the base 81 will all work out okay. The most neatest will be log to the base 3. The other one that will work out quite well is log to the base t. Try that yourself. I'll stick to log to the base 3 here. I don't have to change this one. That's log to the base 3t. Okay, so here's the formula, which I haven't wrote out anywhere. If you want to change the base of anything, it can become log to the base whatever number you want. I'll pick 3, and we keep t up the top, and on the bottom we have to do log to the base again the same number we've made up, and we use this number here. That's the formula basically. The reason I'm using 3, remember what logs are. Logs are log to the base 3 of 9 is actually 3 to the power of what is 9. So that's 3 to the power of 2 is 9. The answer of this is just 2. But again, you put that in your calculator. Next one will be plus, sorry, I don't know why I have an equals here. Should be a plus. Log to the base 3 of t over log to the base 3 of 27. Again, this will be 3 to the power of what is 27? 3 to the power of 3. And remember, you probably should have been noticing that this was 3 squared, 3 cubed, 3 to the power 4. No big deal because your calculator will do this for you, but still it'd be handy to notice. So this bottom row will just become 3. That'll just become 2, just become 3. This one, log to the base 3 of t, is on the top, and the bottom will just become 4, and it will still equal 10. We've lots of things that are the same now. It's just all these bottom rows are nasty. This is a 4, 3, a 2, a 1. We'd like a common bottom row. 12. They all go into 12 quite easily. We could change that into having a 12 on the bottom by multiplying the top by 12. We could get a 12 on the bottom by multiplying by 6. Just once we multiply the top by 6, we're all okay. Multiply the bottom by 4, even it out with the top by 4. Multiply the bottom by 3, top by 3. They all have 12 on the bottom now. So multiply everybody by 12, we really just get 120 over the side. 12 by 10. That destroys all of those guys. It doesn't destroy the new numbers we put on top though, so we can add these all together. 12 plus 6, 18, plus another 4, 22, plus another 3, 25. We get 25 times log to the base 3 t is equal 120. Log to the base 3, I forgot, I needed an extra line here, badly done this, is equal 120 over 25. Let's see, that the 5 goes into both of them, 24 over 5. We want t on its own. How do we get rid of log to the base 3? Logs are easy to get rid of. They're just the opposite of powers. Log to the base 3, if we get, if we put 3 to the power of this, that destroys it and just leaves a t. We just need to do the same to both sides, or in this case, 3 sides. So this will destroy this and we're just left with t. T equals 3 to the power of 24 over 5. And that's the formula we wanted the answer. Part C is actually quite an easy one to do, especially when there's logs up on the board. Explain what log to the base, let's put it up here, log to the base 6 of m means. Well, I already said it in part B. That means 6 to the power of what is equal to m. And that's how you would say that in English, or you could probably write 6 to the power of what, or x, I'd usually put in, is equal to m. I assume they give you full marks for even this, but they usually want a bit of English in that sort of question. In part 2 then, they go on to say, if m is bigger than 6, what does that mean about the value of log to the base 6 of m? So remember, let's say one more time, 6 to the power of what is m? But m is now bigger than 6. So what do you have to get? 6 to the power of what is bigger than 6? Let's put in some numbers. Bigger than 6. Let's put in some numbers up there. 6 to the power of 0.9, 6 to the power of 1, 6 to the power of 1.1. And what are all these equal? This one's easy, it's 6. I jotted down a couple of the others. This is about 7, a little more than 7. This one was about 5. So what does it mean if m is bigger than 6? What has to be up here? It has to be a number bigger than 1. That's one way to say it. Another way sort of hints at the idea of what I did up here. Let's see, this would mean this is equal to x. If m is bigger than 6, that means 6 to the power of x is bigger than 6 to the power of 1. And that means x is bigger than 1. Similar idea as there. Anything like that. Just basically saying x is bigger than 1 is enough for that. But I guess you need to get your head around what the log and the powers mean. I hope that helped. I don't think I explained C part 2 very well. If you have better ideas how to explain it, let me know in the comments. I'll pin it and put it and make sure it's highlighted. And thank you for watching, and have a great day.